Hola.
Hola, Angela. Nice to meet you.
Pleased to meet you. It seems that all works well. I was a little worried.
Just now I see that the Colóquio sent us an email with the link for the talk. Angela, you received by do you enter in the Zoom by the email that you received just now, or you try to use the registration form?
I have received an email from Kirillov, from Professor Kirillov.
Okay.
Some hours ago, yes.
Mm-hmm. I use the registration page, but it's not easy. But by email is better, no? Because you have a link directly to the talk.
Yes. Mm-hmm. That's been very easy.
Mm-hmm. Mm-hmm.
But I tried yesterday to, after having seen the video, the tutorial videos, some days ago, I tried to check if I am able, but it's okay.
Did you use the web page for the Colóquio in the registration?
Yes. But now has been more easy because I simply used the link and then
But I think first, after the first time here, they send some email with the informations, right? The meeting number and the password, if I'm not wrong.
The question is that, at least for me, I tried to check the registration form yesterday, but I can't find the link for the talk. However, there is a logo in the top. Yes. When you click in the logo, there is some update of the page, and so now appear the schedule.
Yes. Indeed, before to understand.
It's not clear.
Yes. But at the end, I understood how to do after some check.
Hey, Angela, in Salento, the university is open or is into closed?
No, now it's closed because now we are in the middle of summer. The university will open at the end of August, more or less. The problem is that now in Salento there are 40, the temperature is very high.
Aha.
40 degrees, more or less.
Oh,
we are, it's horrible. We hope to survive these years.
For us here, this week, it's the last week actually, was, at least for me, very cold.
Cold?
Yeah.
In Brazil, where you are?
Yeah, actually in the south of the country. In the north, it's hot all the time, but for us here in the south of the country, in the last week it was cold.
I like the cold.
Oh yeah.
Yes.
40 degrees, somewhat. Yeah, it's it's very hot.
Yeah, yes. I hope that in the next days the weather is better. I hope. Otherwise, we have to suffer. In the next, we have to suffer more. Ecco. In any way, all this year, the university has been in some sense closed because of the COVID. The most of activities,
for us the same. I believe that during this year,
most of the activity has been given in live, remote, via Zoom or via other systems.
Yeah. Here in my university, we have used Google Meet. It's like Zoom, it's the same.
In my university, Microsoft Teams. We have used Microsoft Teams for the courses, for the lecture.
Angela, do you want to check if your slides can be shared?
Okay. It's okay?
It's okay, yes, yes.
I can put... Now it's better, I think.
Yes, yeah, full screen is better, yeah. We can wait for more than 1 or 2 minutes, okay? We can wait for Alexander Kirillov just for more than 1 or 2 minutes.
I can start when you let me.
Yes, Alexander Kirillov. Okay. Okay, we are in, let me see. Okay, wait just for one minute, okay?
Okay, very good.
Because Alexander Kirillov is trying to enter in the room. I don't know what is the problem.
Yeah.
Oh, okay. So I'd like to thank all of you for attending this conference, in particular this thematic session. It's an honor, it's a pleasure for us, all of you here. Especially, I'd like to thank the speakers for attending this our invitation. And this edition number 33 of the Colóquio of Brazilian Mathematics and Colóquio Brasileiro de Matemática. And this is the first edition of this thematic session, and I hope that we can continue this section in other editions. And this section is about Fourier analysis, complex analysis and applications in PDEs. And it's a great pleasure for me to introduce the first speaker today. It's Professor Angela Albanese from University of Salento, and she will tell about multipliers and convolutors of the space S omega Rn of the omega ultra-differentiable rapidly decreasing function of Bernoulli type.
Thanks. I wish to thank very much the organizer of this section, Professor Dattori and Professor Kirillov, for their kind invitation. In my talk, I will present some results about joint work in collaboration with Claudio Mele of University of Salento. We recall that the study of the space OM of multipliers and of the space OC prime of convolutors, of the space of the classical space S of rapidly decreasing functions was started by Schwarz in 1966. Such a space play a very important role in the classical analysis, especially in the theory of distributions and also in functional analysis for their rich topological structure. Since then, similar spaces were defined and studied in the setting of other classes of spaces of rapidly decreasing infinity function, for example, in the setting of ultra-differentiable function spaces as defined by Komatsu. Following an idea of Gevrey, Komatsu introduced a way to define the ultra-differentiable functions, which consisted in measuring their growth behavior in terms of a weight sequence MFP with certain properties. Later on, Berling introduced another way to measure the growth behavior of infinity functions. Precisely, Berling showed that one can also use weight function omega to measure the smoothness of infinity functions with compact support by the decay properties of their Fourier transform. This approach was modified by Brown, Mice, and Taylor, who proved that these classes can be defined also by the decay behavior of their derivatives by using the Young conjugate of the function omega of e power t. We remark that, in general, the classic defined in the sense of Komatsu cannot be defined following the idea of Brown, Mice, and Taylor. In the last years, the attention of many authors also focused on the study of the spaces omega of the ultra-differentiable rapidly decreasing functions of Bernoulli type, as introduced by Bjork. Inspired by this line of research, our aim was to introduce and study the main properties of the space of multipliers and of the space of convolutors of the space S omega in the setting of ultra-differentiable function spaces in the sense of Brown, Mice, and Taylor. Let me recall some definition results which are useful for the sequel. Following Brown, Mice, and Taylor, we say an quasi-analytic weight function is a continuous increasing function omega from the closed and the bounded interval 0 infinity into itself with the following properties. Omega of q times t is less or equal to k times 1 plus omega of t for every t greater or equal 0 and for some constant k bigger or equal 1. The integral between 1 and infinity of the function omega of t power 1 plus t power 2 is finite. The function omega of t is greater or equal to a plus b times log of 1 plus t for every t greater or equal 0 for some real constant a and a positive constant b. Phi omega t equal omega of v power t is a convex function. the function omega t equal t power s with s between 0 and 1 and omega t equal log of 1 plus t power s with s bigger or equal 1 are simple example of quasi-analytic weight function. Given a non-quasi-analytic weight function omega, the Young conjugate phi omega star or phi omega is the function phi omega star defined by setting phi omega star of s equal this supremum for every s bigger or equal 0. We recall that, given a weight function omega, it's always possible to construct another weight function sigma such that sigma of t is equal to omega of t for t large enough, and sigma of t is equal 0 when t is between 0 and 1. So there is no loss of generality in assuming that omega is equal 0 in the closed interval 0 and 1. Under such assumption, the Young conjugate phi star omega has only negative values. Its Young conjugate is equal to the function phi omega. Moreover, phi omega star is convex, increasing phi star omega of 0 is equal 0, and phi omega star of t over t is an increasing function in the interval 0 infinity. If we take omega t equal t power s, the Young conjugate phi omega star is given by these formulas, as easy to show. Now we can give the definition of the space E omega of capital Omega. In the sequel, omega will be always a non-quasi-analytic weight function. Now, let omega be an open subset of R power n. E omega of capital Omega is the space of all function f which belongs to the space C infinity of capital Omega, such that for each compact subset K of R power n and each positive integer m, the supremum over K of the supremum over alpha of the modulus of the partial derivative of alpha of f of x times this function is finite. We denote this supremum by this symbol. The elements of this space are called omega ultra-differentiable functions of Berlin type on omega. The space E omega of capital Omega is a Fréchet space when it is equipped with the locally convex topology generated by this system of seminorms P, K, M, where K ranges in the set of all compact subset of omega and M in the set of positive integer. E omega prime of omega denotes the topological dual of this space equipped with its strong topology. If we take again omega of t equal t power s with s between 0 and 1, for each positive number lambda and for each multi-index alpha, this function is equal to this quantity. Then, using Stirling formula, it is easy to show that E omega of capital Omega coincide with the so-called small algebraic space of exponent 1 over s. For a compact subset K of R power n, we denote by d omega of K the collection of all ultra-differentiable function of Berlin type on R power n with the support a subset of the compact set K. The omega of K is a Fréchet space with respect to the locally convex topology generated by this sequence PKM of norms. For an open subset capital omega of R power n, we denote by d omega of capital omega the inductive limit over J of this Frechet space, where Kj is any fundamental sequence of compact subset of omega. The elements of this space are called test functions of Berlin type on omega. The element of its topological dual d omega prime of capital omega are called omega ultra distribution of Berlin type on the open set omega. This topological dual is always endowed with its strong topology. We recall now some main properties of this space. The property beta of the weight function omega implies that this space is non-trivial whenever the interior set of the compact set K is non-empty. For any compact subset K of R power n, thanks to the property gamma, we have that the space d omega of K consists of all function f which are C infinity on R power n, such that their support is a subset of K, and for each positive integer m, the integral over R power n of the modulus of the Fourier transform of f times e power m omega of t is finite. Moreover, the space d omega of capital omega is continuously included in the classical space of test function on omega. Such a space is also continuously included in the space E omega of capital omega. Also, the space E omega of capital omega is a locally convex algebra with continuous multiplication, and it is closed under differentiation and contains all polynomials. Now we give the definition of the space of S omega following Bjork. The space S omega of R power n is the collection of all functions f which are integrable on R power n, such that f and its Fourier transform is a C infinity function on R power n, and for each positive real number lambda and for each multi-index alpha, this function are bounded on R power n. The elements of this space are called omega ultra differentiable rapidly decreasing functions of Berlin type. We observe that S omega of R power n is also a Frechet space with respect to the locally convex topology generated by the sequence, this sequence of norms. S omega prime, as usual, denotes the topological dual of S omega endowed with its strong topology. Here we give some properties of the space S omega. The space d omega of R power n is continuously included in the space S omega, and such inclusion has dense range. The property gamma of the weight function omega implies that the space S omega is continuously included in the classical space S of R power n. In particular, if we take omega t equal the function log of 1 plus t, these two spaces coincide. considers topological vector space. The space S omega is closed under convolution, under pointwise multiplication, translation, and modulation. In particular, the Fourier transform F from S omega into S omega is a continuous isomorphism. This isomorphism can be extended in the usual way to its strong dual by setting the Fourier transform of T applied on F equal to T applied to the Fourier transform of the function F. Moreover, if we take a function F in S omega and a distribution T in S omega prime, the convolution of T with F defined in this way is a well-defined function on R power n such that belongs to the space S omega prime, and in particular the Fourier transform of T convolutor F is equal to the Fourier transform of F times the Fourier transform of T. We recall that there are other equivalent systems of seminorms on the space S omega of R power n, as proved by Boiti, Jornet, and Oliaro. Indeed, if we fix F rapidly decreasing function on R power n and P between 1 and infinity, then F is an omega ultra differentiable function, an omega ultra differentiable rapidly decreasing function of Bernoulli type on R power n, if and only if one of the following conditions is satisfied. For each positive number lambda and each multi-index alpha, the LP norm on R power n of this function are finite. Also, for each positive real number lambda, the LP norm on R power n of this function are finite. For each pair of real number, positive real number, lambda and mu, the supremum over all multi-index alpha of the LP norm on R power n of this function times e power minus lambda times phi star omega of modulus of alpha over lambda is finite. In the sequel, this supremum will be denoted by Q lambda mu P. We remark that if P is bigger or equal 1, the condition seen before are also equivalent to this condition. For each pair of positive numbers, lambda and mu, the sum of the series, of this series with the terms, with the term the LP norm power P of this function times e power minus P times lambda phi star omega of modulus of lambda of alpha over lambda is finite. If we consider this series power 1 over P, we denote this quantity in the sequel by sigma lambda mu P. In particular, sigma lambda mu P and also, Q lambda mu P are equivalent system of seminorm of such space. We are ready to give the definition of the space OM omega and OC omega. for m a positive integer and then an integer number, O n omega m denotes the space of false infinity function on R power n such that this supremum is finite. We denote this supremum by Rmn. In particular, Rmn is a norm on this space. In particular, this space endowed with this norm is a Banach space. The space M omega of R power n is defined by setting it equal to the intersection over M of the union over n of the space introduced before. The elements of this space are called slowly increasing functions of Berlin type. Moreover, the space M omega can be equipped with its natural locally convex topology T, given by taking the projective limit over M of the inductive limit over n of the Banach space on omega m. Hence, it is a projective limit of LB space. The space OC omega of R power n is defined by setting it equal to the union over n of the intersection over m of the space O n omega m of R power n. The elements of this space are called very slowly increasing functions of Berlin type. The space OC omega can be equipped with its natural locally convex topology given by taking the inductive limit over n of the projective limit over m of the Banach space on omega m. Hence, it is an LF space. We remark that the property gamma of the weight function omega implies that the space OM omega of R power n is continuously included in the classical space of multipliers OM of Rn introduced by Schwarz, and the same also for the space OC omega. In particular, if we take omega t equal the function log of 1 plus t, the space OM omega and OM and OC omega and OC coincide also as topological vector spaces. The space OM omega is the space of multipliers of the spaces of omega ultra differentiable rapidly decreasing function on R power n. Indeed, we have this result. Fix f a C-infinity function on R power n. Then the following properties are equivalent. F is a slowly increasing function of Berlin type on R power n if and only if for every g in S omega and for every positive integer m, we have that the supremum over alpha of the supremum over x of the modulus of g of x times the partial derivative of order alpha of f of x times this function is finite. We denote this supremum by qmg of f. Moreover, these conditions are equivalent to for every g in S omega the function f times g is also in S omega, which is equivalent to for every t in the dual space S omega prime, ultra distribution f times t is also in the space S omega prime. Moreover, if we fix f in the space OM omega, the operator MF from S omega into S omega defined by setting MF of G is equal to F times G is a continuous linear operator from S omega into S omega. And hence, the operator call M of F from S omega prime into S omega prime defined by setting call M of F, call MF of T equal F times T is continuous. The continuity of this last operator is easy to show because it is the topological dual of the operator MF. The proof of the fact if F belongs to the space OM omega implies that for every G in S omega, F times G belongs to S omega is in some sense is easy because it depends to the definition of the space OM omega and of the space S omega. It is more involved the proof of the implication 3 implies 1. For this, we give here a sketch. The proof of this implication relies on these two facts. Fact 1, let f is infinity function on R power n. If f times g belongs to the space S omega for every g in S omega, then the function f is necessarily an omega ultra differentiable function of Bernoulli type on R power n. Fact 2, let rho an element of the space d omega of R power n such that its support is a subset of the open ball of center 0 and radius 1, and let xj a sequence of points satisfying this condition. If we consider the function g defined by this formula, then one shows that G is also in the space S omega. Now, assume that the condition 3 is satisfied. Then, by fact 1, the function f belongs to this space. Suppose that f is not a slowly increasing function of Bernoulli type on R power n. Then, combining this fact, we are able to show that there exists a positive integer m such that for each pair of positive real numbers C and R, and each positive integer n, there exists a point x with modulus bigger than R and a multi-index alpha, such that the partial derivative for the alpha of f of x in modulus is bigger or equal of this quantity. Now, proceeding by induction, using the previous inequality, we can find two sequences alpha j of multi-indices and xj, with xj satisfying this condition, such that the partial derivative for the alpha j of f of xj is greater or equal to this quantity. Now we fix a function rho in the omega of r power n with the support a subset of the open ball of center 0 and radius 1, such that rho is equal 1 on the open ball of center 0 and radius r for some r between 0 and 1. Then, if we consider the function g of x so defined, by the fact 1, this function belongs to the space S omega of r power n. And then, by our assumption, f times g is also in this space, and then the semi-norm QMM of f times g is finite. Therefore, this quantity is also finite because it's less or equal to QMM of f times g. Now we observe that for every j, the function g is equal to this constant in the closed ball of center xj and radius r, recalling the definition of the function g and and the property of the function rho. Therefore, on this closed ball, the partial derivative of order alpha of the function f times g is equal to this constant times the partial derivative of order alpha of the function f for every multi-index alpha and for every g. Therefore, taking into account this equality and inequality 8 and 9 seen before, it follows that this supremum, which is finite because is less or equal to QMM of f times g, is greater or equal to this supremum. Then the supremum of this sequence is finite. But this sequence goes to infinity when j goes to infinity. And hence we obtain a contradiction. Then the proof of 3 implies 1 is complete. What are the other properties of this space? The other properties are the following one. The set of the semi-norms Q, M, G, where M ranges in the set of positive number and G in the space S omega, defines another locally convex topology tau on this space. This topology is weaker than T. Now, if we use the fact that the topology tau is weaker than the topology T, the space of M omega endowed with the topology T and the space of M omega endowed with the topology tau have the same bounded set, and we apply a recent deep result of the Breuer-Nate, we can conclude that these two topology coincide. Therefore, the locally convex topology T can be described by means of this system of norms. These all inclusions are well defined and have dense range. By duality, also these other inclusions are well defined and continuous. Moreover, the space OM omega of R power n is continuously included in the space S omega prime, and then, in view of this fact, also the space OC omega of R power n is continuously included in the space S omega prime. We now show that the elements of these two spaces can be defined also in terms of weighted LP norms with P bigger or equal 1. This fact, this description, permit to obtain in an easy way some suction theorem for their strong dual spaces. The definition, the following definition is analog to the definition seen before for the space OM omega and OC omega. Actually, let B bigger or equal 1. For M, a positive integer number, and N, an integer number, ON omega PM of R power n denotes the space of all functions C infinity of R power n with the following property: this series converges, where the term is the LP norm on R power n power P of this function times E power minus MP phi star omega of modulus of alpha over n. We denote the sum of this series power 1 over P by R MNP. R MNP is a norm on this space, and in particular this space with this norm is a Banach space. As did before, we denote by OM omega P the space given by taking the intersection over M of the union over N of the space ON omega P M. In such a way, the space OM omega P can be equipped with the locally convex topology given by taking the projective limit over M of the inductive limit over N of these Banach spaces. The space OC omega P is defined by setting it equal to the union over N of the intersection over M of the space ON omega P M. Also, in this case, the space OC omega P can be endowed with, in a natural way, with the locally convex topology given by taking the inductive limit over N of the projective limit over M of this Banach space. Now, the following result also. Let B P bigger or equal 1. Then the space OM omega and the space OM omega P coincide as a topological vector space. The same is also true for the space OC omega and OC omega P. For the proof of this theorem, is given by showing first that the space OM omega is continuously included in the space O M omega P, and also the space OC omega is continuously included in the space OC omega P by using the properties of the LP norms and the topological structure of these spaces. While to prove that such inclusions are also surjective and open, it's necessary to an appropriate Morris bending theorem, which states that if k times p is bigger than n, where k is positive integers and p is bigger or equal 1, then for each positive number, integer number n, there exists another integer number n prime greater or equal n, and a positive constant c, such that the L infinity norm on R power n of the function f times e power minus n prime times omega is less or equal to the constant c times this norm, where this norm is defined in this way. That is equal to the sum over all multi-indices alpha with modulus less or equal k of the LP norm R power n of the function e power minus 1 n times omega times the partial derivative of order alpha of f. Now, using the description of the space of M omega and OC omega in terms of LP norm and using standard tools of function analysis, it is easy to show these structure theorems. Precisely, let T in an omega ultra distribution of Berlin type on Rn and P bigger or equal 1. Then T belongs to the dual space of the space OM omega if and only if there exists a positive integer m such that for every positive integer n there exists a sequence f alpha in this weighted LP prime space, where P prime is the conjugate exponent of P, such that T is equal this series, where the general term is the partial derivative of order alpha in the sense of distribution of the function f alpha. And this sequence satisfies this inequality that this series is finite in case P prime is between 1 and infinity, while in the case P prime is equal to infinity, this supremum is finite. Also, we have also a structure theorem for the topological dual of the space OC omega prime. Actually, let T in D omega prime and P bigger or equal 1, then T belongs to the dual of the space OC omega if and only if for each positive integer n there exists a positive integer n and the sequence f alpha in this weighted LP prime space, such that again T is equal to the sum of this series And the sequence satisfy inequality 15 if p prime is between 1 and infinity, while satisfy inequality, this other inequality in case p prime 16 is equal to infinity. Finally, the structure theorem for the space S omega prime is the following one. T is always in this space and P is bigger or equal 1. Then T belongs to the topological dual of the space S omega if and only if there exists a positive integer m and F alpha is a sequence which belongs to the weighted LP prime space such that T is equal to this sum. And in this case, the sequence F alpha is such that this series is finite in case P prime is between 1 and infinity, while in the case P prime is equal to infinity, is this supremum finite. Now, using, I have my time is up. Finally, using this structure theorem, it's possible to show the fact that OC omega prime is the space of convolutors. Precisely. Let T in this space and consider the following properties. T belongs to the dual of the space OC omega, and the property T for every F in S omega, the convolution of T between F with F belongs to the space S omega. Then 1 implies always 2. If we assume, in addition, that the weight function omega satisfies this condition, then property 2 implies property 1. Therefore, this means that this space is the space of convolutors. Moreover, if we fix T in this dual space, the operator Ct from S omega and S omega defined by setting Ct of F equal to T convolutor F is a continuous linear operator. Because we have no other time, I have to skip the idea of the proof, and we observe that since OC omega prime is the space of convolutors of the space S omega, if we take an element S in S omega prime, we can define the convolution of T with S by setting T convolutor S applied on F equal to S applied to this function, and this function belongs to the space S omega. And in particular, we have that T convolutor S belongs to the space S omega prime for every S in S omega prime. In particular, the operator call Ct defined by setting call Ct of S equal to T convolutor S is continuous, because it is the topological dual of the operator Ct. And finally, we have this fact which shows what is the relation between the space OC omega prime and the space OM omega. Actually, under the condition that the function omega satisfy this condition, the Fourier transform F is a topological isomorphism from the space OC omega prime onto the space OM omega of R power n. Moreover, we have the following formulas. The Fourier transform of T convolutor S is equal to the Fourier transform of T times the Fourier transform of S, and the Fourier transform of F times T is equal to 2 pi minus n, the Fourier transform of F convolutor the Fourier transform of T. This is all. Then I would like to thank you very much for your attention.
Thank you, Angela. Very nice talk. We have time for a short question and for a short answer, of course. Question or comments?
Paulo.
Opa.
Hi, Professor Angela. I'm sorry for lost your beginning of your presentation. I watched by YouTube, but I had a problem to connect by Zoom, but now it's solved. Are you using this to study solvability of equations, or in the first, at this time, you are just studying the structure of this space?
No, I have not studied the topics of solvability in this setting. We have only introduced and studied the main property, their structure topology, nothing else. No more. At this stage.
Okay.
In the future, maybe.
Yes. You have all the structure necessary to study.
Yes.
All the tools. Okay, thank you.
More comments or questions? If not, we can please. Thanks, Angela.
Thank you.
Thank you. Wagner, do you want to try to share your presentation? Sure. Okay. Okay, so the next speaker is Wagner Augusto Almeida de Moraes from Ghent University, and he will tell about the global properties of Fourier multipliers in the non-harmonic analysis setting.
Thank you, Paulo. Thank you also, Alexandre Kirilov, for the invitation for me to give this talk here in the Colóquio Brasileiro in Matemática. It's a really pleasure for me. So today I'll talk about the global properties of Fourier multipliers in the non-harmonic analysis setting. And this term, non-harmonic analysis setting, appears firstly by the work of Pelle when they are studying some system on the torus T2 of the exponential of 2 pi I lambda x, but lambda not integer as usual, but lambda being any real numbers. And recently, in 2016, Michael Huzansky and Mias Tokmagambetov, they gave a global analysis in this setting of the non-harmonic analysis. So first, I'll introduce an example. And with this example, we can think in the general setting easily. So first, we begin with omega, the unit square in R2, and we consider H, a vector on R2, positive. Positive means that both components are greater than 0. And we consider this operator LH on omega, given by this expression, that is essentially the Laplacian, right? But here we consider different boundary conditions. So with this vector H that we consider first, we take these both boundary conditions. So when we apply 0 on the first variable and multiply by H1, we obtain the function apply on 1 in the first variable, and also for the derivative of respect to the first component, and H2, the same applying for the second variable. So we consider the domain of this operator, all the function on L2, such that when we apply the Laplacian, we obtain again an L2 function, and F must satisfy this boundary condition. So we see here that the adjoint of the operator LH will be LH minus 1, where the inverse of H is the inverse of each component. So this operator LH is self-adjoint if and only if H is equal 1, 1. And in this case, when H is equal 1, 1, we have periodic conditions here. So essentially, we are working on the torus setting, on the torus T2 setting, when H is equal 1, 1. And this is usually what happens in the theory. So when we are working on compact manifolds and the torus and compact Lie groups, we always start with, almost always start, right, with a pseudo-differential operator that is self-adjoint, it's a positive actually. And we use this operator to decompose the space L2 as a sum of finite dimensional subspaces, and these subspaces will be the eigenspace of this operator, and on. But here, the operator LH is self-adjoint if and only if H is equal 1, 1, and for the other cases. So we also have some good knowledge about the spectral theory about this operator. So we know who is their eigenvalues, their eigenfunctions. So the eigenfunctions of the operator LH we can index with Z2. So it's given by this expression. So when H is equal 1, 1, 1 is the usually that we know from the torus. And the eigenvalues is given by this expression. And again, appear this log here. And when H is equal 1, 1, this log disappear, and we obtain, we know in the torus setting, this minus 4p squared, then the norm of xi. So here, this expression h power x means this, h1 power x1, h2 power x2. And we have that these functions, these eigenfunctions, is a basis for the space L2. But it's not an orthogonal basis when do the inner product on L2 of two different eigenfunctions is not 0. And here, since it's not self-adjoint in general, we can also study the spectral theory, spectral properties for the adjoint operator LH star. And we know that the eigenvalues will be the conjugate of the eigenvalues of the first operator. And we denote by VXC the eigenfunctions for the adjoint. And here is almost the same, but here, as we saw first, the adjoint is H minus 1. And here, we also have that this VXC is a basis for the L2. And these two bases, they are orthogonal. That is, when we do the inner product for a function for one basis given by uxi, and another function given by the basis given by the adjoint v eta, we obtain they are 0 if h is different from eta, and they are equal 1 if c is equal eta. So these two bases, we call them biorthogonal system. So for every function L2, since uxi is a basis, we can write this way, and we know who are the coefficients. So it's the inner product of f by the vxc given by the adjoint, and we denote this by the Fourier coefficient of f with respect to c. And also using the other bases given by the adjoint, we have the coefficients is given by the inner product of f with uxi given by the first basis, and we call these coefficients as the f star, the L star Fourier coefficients of f at c. And so we can write f in this way. And when h is equal 1, 1, we have that if you take the intersection of all the domains of all the powers of the operator LH, we obtain actually the smooth functions on T2. So this is what happens in this first example. Now we are talking about general setting. So always thinking about this example to understand better the concepts. So here we'll start with omega, connect bounded open subset of Rn. And L we consider a differential operator of order m with smooth coefficients in omega, equipped with some linear bounded conditions Bc. That is, the space of functions satisfying this boundary condition is linear. And this happens in the previous example. So we will assume that L has a distracted spectrum where the disk C is given by this set of indexes, and we can always think about as a subset of some zk. And we ask that these eigenvalues goes to infinity when C goes to infinity. And we can also order the eigenvalues in the ascending order. So we denote the eigenfunctions of L with respect to lambda C by uxc, and this uxc will satisfy the boundary condition because they are in the domain of L. And the conjugate spectral problem of L is given by this, is the spectral problem for the adjoint, and we know that the eigenvalues will be the conjugate of the original one, and we denote by vxc the eigenfunctions. So in general, this operator L does not have to be self-adjoint, neither elliptic, actually. And we always can take a biorthogonal system, uxc and vxc, and here we can normalize, if you want, the functions. But the important thing here is that they have this property. They are a biorthogonal system, as we had seen before. So we assume that the eigenfunctions of the operator L is a basis for L2. So with this assumption, we have that the eigenfunctions for the L star will be also a basis for L2. So we just need to assume one of them to be a basis, that the other one will be a basis also automatically. So here we'll define what will be our smooth function in this setting, but to not be misunderstand what is happening here, I prefer to call them with H, not C infinity, because sometimes for some operator L, the elements of this set probably will not be a smooth function. So the space H infinity L is called the space of test functions for L, or L test functions, and is given by the intersection of the domain of all the powers of the operator L. And we see the first example when H is equal 1, 1, this coincides with the smooth functions on the torus T2. And here we can gave the usual Frechet topology given by this family of semi-norms. And since the operator L is not self-adjoint, we can also talk about the L star test functions. Then we switch L by the adjoint of L. And the boundary condition we substitute by the boundary condition star, the conjugate boundary condition. So for F, L test function and G, an L star test function, we have this kind of duality. And this motivates us to define the L distributions being the linear continuous functions on HL star. So it's different. So it's not what we are expecting at first, as first view. So the L distributions will be linear continuous functions on H infinity L star. So for an L distribution, we will denote the action on phi by this way, with these brackets. And for any psi L test function, we can define an L distribution induced by this psi given by the usual, the integrate of the product of them. And this gave us an embedding from the L test functions into the L distributions. And analogously, we can define the L star distributions. So to talk about the Fourier transform, we will also ask this additional property for the boundary conditions, which means that if you have a sequence of functions on H infinity L0, this L0 could be in L or L star that converge, then the limit will be also an element of H, will be also a L0 test function. So this will help us to commute the limits with series, because then the convergence will be uniform in this sense. So for F, an L2 function, we define the L Fourier transform of F at C by this expression that was motivated by the first example. So it's just the inner product of an L2 of F with the elements of the basis given by the L star, by the adjoint of L. Then we can written F by this series here. And it's converged because our additional property that we had said before. And similarly, we can define the L star Fourier transform of F at C being the inner product of F with the elements of the basis of the eigenfunctions of L. And also, we have these expressions for this kind of inverse Fourier transform for F hat star. And if we have an L distribution, we can also define its L Fourier transform at C given by this expression. So it will be the action of W in the conjugate of VC. Then we can write W also as this series with the convergence in the space of the L distributions. And if W is given by an L test function, these definitions agree with the definition before for just L test functions, right? And similarly, we define the same for the L star distributions, just switching V by U, right? So now, if we start with a function A, where the domain is our set of index, and we define this series. When this series will converge, or when this will define an L test function or an L distribution, so we need to study the behavior of this function A. So we'll denote it by S, Y, be the space of rapidly decayed functions phi. So that is phi will be a rapidly decay function if for any m greater than 0 there exists a constant that depends on m, such that we have this this control of the growth of our function phi. And S prime will be the space of moderate growth functions. That is, phi will be a moderate growth function if there exists constant C and M such that this happens. In this quantity here, this Japanese bracket of Xi is defined by this expression. That is pretty common in the analysis, Fourier analysis in our harmonic setting also. So consider the L Fourier transform. So if we can see the Fourier transform as a function with domain in the set of indexes, and also the L star Fourier transform given by this FL star, we have, this was proven by Rosansky and Tokmagambetov, that the L Fourier transform is a bijective homomorphism from the space of L test functions to the space of rapidly decayed functions, and also from the space of L distributions to the space of the moderate growth function. And the L star Fourier transform is a bijective homomorphism from the space of L star test functions to the same set of the space of rapidly decaying functions, and from the L star distributions to the set of the space of the moderate growth functions. So here's a characterization of L test functions and L distributions. So F will be an L test function if and only if for any n greater than 0 there exists a Cn such that the Fourier coefficients of F satisfy this inequality, and similarly for the L distributions. Here we don't have, in this setting, we don't have equalities here with m and k equal 1. So the sum of the square of the Fourier coefficients will not be equal the L2 norm of F square, but we have these inequalities here that will be enough for our analysis. Actually, we have a Plancherel identity, but here in this series, not the absolute value square, but it's actually the Fourier coefficient of F times the Fourier coefficient of F star. Then we will have the equality for the Plancherel identity. So about quantization in full symbol, I will just talk, I will summarize really quickly, because in this talk, I will just talk about L Fourier multipliers. I will not talk about general space of symbols or of amplitudes, but it's all in the paper by Rosansky and Tokmagambetov in this general setting. But here we assume that there exists an S0, a real number, such that this series converges. This is useful to prove some convergence later. So let A be a continuous linear operator of L test functions. So we define its symbol, sigma A, as this function from omega times I to C, given by this expression. So usually this U is different from 0, then we can make this power -1. When this is equal to 0, there is another way to define the symbol, but here in this context, that doesn't matter. So here we have that we can quantize the operator A in this form. So A applied to F, given by this series, where here appears the symbol of A. And similar, we define the symbol of continuous linear operator where from L star test functions, right? And we also have this quantization. Repetition here, we are talking about the L Fourier transform, and here appears the UXI, and we're talking about L star, here appears the L star Fourier coefficient and the function V, right? So what will be our object of study will be Fourier multipliers. So Fourier multipliers will be continuous linear operator, which symbol does not depend on X. So here, the symbol will not depend on X. So here in this series, we see that the Fourier coefficient of AF is just the product of the symbol by the Fourier coefficients of F. And B will be a L star Fourier multiplier. Also, if its symbol does not depend on X, then the Fourier coefficient of BF star will be the product of the symbol by the Fourier star coefficient of F, right? And an interesting thing here is that if we start with a continuous linear operator, A, on L test functions, this operator A will be an L Fourier multiplier with symbol sigma A, if and only if its adjoint A star is an L star Fourier multiplier with symbol conjugate of sigma A. And we can, and if you have an L Fourier multiplier, we can extend it to the space of L distributions in this way. And this extension will also has the same property. The Fourier coefficient of AW is the product of the symbol by the Fourier coefficient of W for all W Nelly distribution, and the same for the L star. Right, so now we'll talk about some global properties of Fourier multipliers in this setting. So we say that an operator P of L distributions here is globally L hyperelliptic if the conditions W L distributions PW an L test function implies that our initial L distribution is actually an L test function. So here, obtain this first characterization. So let P be an L Fourier multiplier with symbol sigma P. Then P is a globally L hyperelliptic if and only if there exists some m greater than 0, that we have this behavior of the symbol from some point on the Japanese bracket of Xi. So in particular, the symbol will be different from 0 only for a finite many elements of our setting I. And similarly, we define the global L star hyperellipticity if the conditions, the same conditions, but now for L star. And again, P will be an L star Fourier multiplier will be globally L star hyperelliptic if and only if satisfies the same kind of property. And an interesting corollary is that if P is an L Fourier multiplier, P will be globally L hyperelliptic if and only if its adjoint P star is globally L star hyperelliptic. This happens because the symbol of the operator, the operator P star is just the conjugate of the symbol of the operator P. Then if satisfy the condition of one theorem, it will satisfy also the other theorem. And about solvability, first we need to talk about what functions we can put here in the right-hand side. So if PW is equal F for some L distribution, the Fourier coefficients of F must satisfy this equality, right? Because P is a Fourier multiplier. So we denote E, the space of L distributions that satisfy these conditions, because when the symbol is equal 0, then if PW is equal F, the Fourier coefficient of F at Xi must be also 0. So we denote the space of L distribution that satisfies this, that has this property. We call these distributions as admissible L distributions. And we will say that an operator P is globally L solvable if the image of the operator P is exactly the space of admissible L distributions. So that is, if for any P admissible L distribution F, there exists an L distribution W such that PW is equal F. So our first theorem here is that P is globally L solvable if and only if there exists an M greater than 0 such that the symbol has this property. It's pretty similar for the global hyperlipticity, but here I just ask this property whenever the symbol is different from 0. So here can happen that the symbol can be 0 infinitely many times, right? And a corollary is that if P is an L Fourier multiplier symbol sigma P, if P is globally L hyperelliptic, then P is globally L solvable, because these conditions imply the condition on the solvability. And we have the same results for the L star function, right? And since we have the same kind of behavior here, the symbol, we also have this corollary. So if P is globally L solvable, if and only if P star is globally L star solvable. Right, so let's go back to our first example. Here, I just would take attention here in the expression of our Japanese bracket C in this setting. So we would need to take an absolute value here, this expression for lambda C, then take a square, sum 1 and power 1 over 4. So we don't need to do this because we have these propositions. We can compare this Japanese bracket with this well-known quantity, right? So we can just make proofs with this quantity, not with the previous one gave by the eigenvalues of the operator LH. So here we have this property about the Fourier coefficients of the derivatives in this setting. So if F in an LH test function, here this H can be any H. It's not just 1, 1 or different for 1, 1. It's just H greater than 0. We have this expression for the Fourier coefficients of the derivative. So again, if H is equal 1 is what we know about the periodic situation, but when we are not in the periodic situation, appear this logarithm of Hj. Here's just a sketch of the proof. I'll skip because the time. So here we consider this operator P, given by these expressions, is the first derivative plus C, the second derivative. It's with C a complex number different from 0. This is a well-known operator that is being studied since the 70s. And when H is equal 1, 1, we are in the torus setting. And we know when this operator is globally hyperelliptic and globally solvable. So there are many papers that study these global properties for operators like this in the torus, T2 or Tn. I just picked 2 of them here. So the Greenfield-Walker 72 is the first one that appears this result, and the Huni in 79 gave a lot of characterization about the solvability of this operator. So here the operator P in the torus T2 when H is equal 1, 1 is globally hyperelliptic if and only if either the imaginary part of C is different from 0 or C is an irrational non-Liouville number. Moreover, the operator P is globally solvable if and only if either an imaginary part of C is different from 0 or C is a rational number. So here appears a different condition. Oops. Or C is an irrational non-Liouville number. And here I tap the definition of Liouville number. Even with it, we always work with non-Liouville number. But the Liouville number is a real number Y with this property that we can say that they are irrational numbers that are almost rational. We can think in this sense, right? Right, so we know what happens when H is equal 1, 1, but in the general setting for any H positive, what happens? So when we apply the Fourier, when we compute the Fourier coefficients, we obtain this expression here. So in setting C equal A plus IB, we obtain that P is a LH Fourier multiplier with symbol sigma P, and we have this expression for the symbol of our operator P. So here appears some logarithms of that involves H1, H2, and also the number C, A here and B here. So when H is equal 1, 1, these logs doesn't appear, and we are in the torus setting. But here, in general, if we assume that we have this property, C log H2 different or minus log H1, so we have that this operator is globally LH hyperelliptic. So even if C is a Liouville number, is a rational number, here doesn't matter. If we have this property, then the operator P will be globally LH hyperelliptic. And notice that we don't have any contradiction, what we already know from the torus, because from the torus we don't have these conditions, because in the torus we have 1, 1, so the log will be 0, 0. So we are not in the torus setting here. Since this operator are LH, global LH hyperelliptic, then we will be also globally LH solvable from the previous theorem. Right, so, and what happens when we have the equality? Oh, I think I have time just to give a little sketch of the proof. So if we have this hypothesis, we can write with C is equal A plus IB. So this means this, that imply that this complex number is different from 0. So if it's different from 0, we have two cases to consider. First one, the real part is different from 0, that is H1, H2 power A is different from 1. So in this case, this logarithm is different from 0, that appears here in the expression for the symbol. And this implies that this symbol vanishes for at most one C in Z2, because this part here is different from 0. So first we will need to solve an equation on C2, and if this solution is integer, then we have to solve another equation here to obtain an H1, and if this C1 is integer, then we have a C such that the symbol is equal to 0. And moreover, we also can obtain a constant such that this happens whenever the symbol is different from 0. But it's different from 0 almost always. There's just one value that could be 0. So in this case, we have this kind of control of the Fourier coefficients of W So if PW is an L-test function, so PW hat will be an element of S that is a rapidly decay function, then W will also be a rapidly decay function. So in this situation, P is globally LH hyperelliptic. In the case 2 is that this is 0, but this part is different from 0. That means that B must be different from 0. And then the analysis is pretty the same. So this will be 0 even only if H2 is equal to 0, and then we have to solve our equation here, and we'll obtain at most one, still one, that the symbol will be equal to 0. So the operator P is globally LH hyperelliptic. So now in this situation, when C log H2 is equal minus log H1. So in this case, the operator P will be globally LH hyperelliptic if and only if we have the same situation on the torus. The imaginary part of C is different from 0, or C is an irrational non-Liouville number. And moreover, the operator P is globally LH solvable if and only if either imaginary part of C is different from 0, or C is a rational number, or rational number, or C is an irrational non-Liouville number. So to obtain this result, first we'll take a look at the hypothesis. So if this is 0 equal to 0, means that we are in the 1-1 situation. So if H is equal 1-1, then this hypothesis holds for all C, right? And then the result was already proved by Greenfield-Wallach. And if H is different from 1-1, so we are not in the situation 0-0. So here appears an imaginary number, and here appears a real number. So the imaginary part of C, that is B, must be 0, and C must be this fraction, minus log H1 over log H2. So in this situation, if you substitute these numbers here in the expression for the symbol, we obtain that the symbol of the operator P is just this expression. That is the same for the torus. So by our previous theorem, the operator P is globally LH hyperelliptic if and only if there exists an m greater than 0, such that this happens. And this is exactly the case when the number A is an irrational non-Liouville number. And for the LH solvability, we don't have this condition here. Then we also have this property for a rational number when this expression is different from 0. Okay, so we talk about constant coefficient operator here. We can also think about when C is a function on the first variable, but which function? So actually we cannot take C as an L-test function, because if we make the multiplication pointwise of two LH test functions, we don't have an LH test function usually. But what we have is that this space of LH test functions is a C-infinity T2 modulo. That is, if you take an LH test function and a smooth function on the torus T2, so the function AF will be an LH test function. So here we can consider, so this operator. Here, A is just a real valued function first on the torus T1, and we consider this operator P. This is well defined because of our previous proposition. And we take A0, the average of A, right? So the integral from 0 to 1 of A, and we consider this operator P0 with constant coefficients. So the operator P, this one, if variable coefficients A, is globally LH hyperelliptic, if and only if the operator P0 is globally LH hyperelliptic. This is something that happens on the torus when h is equal to 1, and also happens for any h. And the same for the global solvability. Right, so here's the main reference of this work. The main of them is this work from Ruzansky, Tokman, and Beethoven, non-harmonic analysis of boundary value problems. And here is the preprint that I put on archive about these results. So thank you very much.
Thank you, Wagner. We have time just a comment or a short question if you want to have some questions or comments.
I would like to do one question, but Wagner, I liked very much of your work. Very nice presentation. Your examples explained it to me. Most of the questions were answered by your example, so it was well planned, your presentation. So you don't have nothing about an invariance theorem about this new concept of hyperellipticity, you know? Because if you prove that the operator is LEH hyperelliptic with respect to one operator, you cannot transport this property to another operator. Is that right? No. Depend on
with respect to h, you mean?
Respect to the L operator. Because you use an operator to construct these spaces.
Oh, yeah.
But if you prove with respect to one operator, the hyperellipticity, you cannot transport the another.
Oh, yeah. No.
So you cannot use this. You cannot use this a specific operator to prove the global hyperellipticity, for example, and for the general case or for.
Oh, yeah. It always depends of the choose of the operator L.
And
we can see
operator
this.
L, okay. And this operator L is any operator. You don't ask linearity, nothing about them.
First, it's a different linear operator with order M. Oh, just in the beginning. Here is a differential, a linear operator. I forgot the linear here. Linear operator of order M.
I was thinking that it was possible to use this to study maybe non-linear operator, but this is not possible.
Yeah.
Okay. I have a lot of questions, but I can ask you another situation. Thank you.
Thank you.
Okay, so let's thank Wagner again.
Thank you, Al.
In the schedule, we have a break for 10 minutes, but for today, we are late. And so maybe it would be nice if we do a break for 3 minutes for a break, okay? Just to take a coffee.
Yes,
okay?
Thank you.
Good idea.
Oh, let me stop share.
Okay, we can return in 3 minutes.
Okay.
Okay. Fernando, do you want to share your presentation? Mm-hmm.
Share screen. This is not this one. Not this one.
Mm-hmm.
This one. Can you see now?
Yeah, but you can. It's better if you put in the full screen.
Okay.
Ah, it's nice. Mm-hmm.
Right.
Mm-hmm. Mm-hmm. Okay. After the talks, this link of the Zoom will keep open for more than 1 hour, and so all of you are invited to keep here for conversation, just for the social conversation. Of course, you can ask about mathematics anyway. Okay, so the next speaker is Fernando de Ávila Silva from Federal University of Paraná, and he will tell about time periodic Gelfand-Shilov space and global hypoelites for a class of evolution equations.
Okay, thank you, Paulo. And now I find a typo at the title. Okay. So thank you, Paulo. Thank you, Kirillov, for this for the invitation. I'm very, very happy with this opportunity. And today I will share some results obtained in collaboration with Professor Marco Capiello from the University of Turin. These results are part of a work that it's now an epsilon from the submission. It's almost finished, okay? But there is some nice result that I would like to share with you, okay? The main idea here is to introduce a class of functions where the time variable belongs to the torus and the variable x belongs to Rn, right? That's why the title, time periodic Gelfand-Shilov space, and I will explain you in a few slides why I consider this type of spaces here. But if you see here, somehow this is essentially a space where on T belongs to some Gevrey classes on the torus, and on variable x belongs to the symmetric Gelfand-Shilov spaces. Okay, our idea is to present some Fourier analysis for this space. In short means some expansion on X, right? Some kind of partial Fourier analysis, right? And as an application, I will present some results connected with the global hypolepticity, right? Okay, just some motivations. The first is this work of Professor Rony from 1979, where he considered this type of operator here, an abstract operator. L is dt plus bt a plus some r. A here, a nice operator defined on a Hilbert space with good eigenvalues, and R is some low order term, some suitable sense. Okay, but something very, very interesting in this work, well, is this observation, is the remark that the spectrum of the operator A, it's not important for the study of solvability and hypolepticity, but it is in case when it's not important when T belongs to some interval, but it's important when we are considering T belongs to the torus. This is one of the reasons that I'm considered this type of operators, dt with T belongs to the torus, bt plus some other operators. This is one of the reasons. And the other reason is because it's very fun to work with these problems here. And this behavior at infinity, it's essentially some, it's connected with some Diophantine approximations. Okay, as an example of this operator here, for instance, we consider the problems and the torus, the two-dimensional torus, we may think in this case the Hilbert spaces as the L2 spaces, and the operator A as some extension of dx. Okay, and in this case we can consider these Fourier representations for elements on the distributions, U as a distribution, F as an smooth function, and then this equation, an equation LU equals to F, is then equivalent to a sequence of ODEs. Okay, and what we need to do here is to prove that this solutions UT psi goes to all derivatives goes to 0 faster than any polynomial, right? This is some basic result from this Fourier series on the torus. Okay, and when we have here psi C0, if this psi C0 is not an integer number, okay, the solutions of this equation, one is given in this equivalent two ways. Okay, here we can see some Diophantine approximations. I mean, how fast this term goes to 1, or this exponential goes to 1, or how fast this part here goes to 0. This is important. And this is essentially the approximation of real numbers by rational numbers. And for this exponential term here, if you consider models of this exponential, we have exponential of psi integral of the imaginary part of C. And then we have here some connections with the so-called Nirenberg-Treves conditions. I mean here some change of sign is important, okay? But something interesting here is that we are considering some partial Fourier expression here, Fourier on X, right? And a second motivation is this work in collaboration with Kirillov and Grantchev. This was the work of my thesis. And the idea is to consider this operator, dt, plus some pseudo-differential operator C. Here we are considering the setting here, operator C belongs to some class of pseudo-differential operators on M. M here, a smooth compact manifold without border, essentially a closed manifold. And with C commuting with some elliptic operator, okay? In this, of course, for an elliptic operator, there exists a basis given by its eigenfunctions. All eigenspaces are finite dimensional, and it's possible for functions on the L2 to obtain some Fourier expansions. But when you consider here T product by M, we obtain some expansions for elements in C infinity T product by M. Okay. This is somehow connected with the work of Wagner, the last talk, in some sense. This is the same. There's some connections here. Okay, but something important here is the following. If you consider the simple case, C is essentially a product of this product, CT by the elliptic operator. Then the equation LU equals to F. Is equivalent to the system of these diagonal systems, right? Where this capital lambda is essentially ICT product by the eigenvalues of the elliptic operator E, and here we have some where I is the identity matrix, okay? In this case, as in the case of two-dimensional torus, what we need here is to prove that all derivatives of these vectors, uj goes to 0 faster than any polynomial. Okay, we obtain a similar approach here. But something different happens when we consider CT product by P, where P now commutes with A, right? In this case, we have some invariance for the eigenspaces of the operator A. And if we represent this invariance on the for this eigenspace as a matrix, we obtain the systems here. Okay. Something interesting in this case is that, for instance, of course, now we need to study the eigenvalues of this matrix Pj, but now change of sign for the imaginary part of C is not so important. I mean, it's possible to obtain operators globally hyperelliptic where the imaginary part of CT change sign, for instance. Okay, but this is a discussion for another opportunity. But what really matters here is some Fourier expansion on the variable x. Okay, and after this work, I was thinking for a long time, okay, but if I replace the manifold, the compact manifold, but some manifold that is not compact, right? For instance, if you replace by Rn, the dimension, the Euclidean space Rn, okay? What we can do in this case? For instance, something, of course, we can consider is the regularity of solution, but also since we are in the Rn, we may consider the decay at infinity, right? We can both control this, the regularity and decay at infinity. And a good place to do this is the Gelfand-Schilov setting, okay? And this is the reason we have this collaboration between me and Professor Capello. Professor Capello knows, he is an expert on this, Gelfand-Schilov spaces. And after some discussions, we start the study for this paper we finish. Okay. So for this talk, I will talk a little bit about this Gelfand-Schilov space. What is important here is the eigenfunctions functions. I will talk about this time period Gelfand-Schilov spaces as an application, the global hyperellipse. Okay. Well, I have here some introduction for and was introducing this space, okay? But these are spaces defined on Rn smooth functions, which are here, if you look this inequality here, we have some G regularity, okay? And also this exponential decay, okay? So we can study both phenomena. Regularity and decay at infinity, right? Okay. Something important here is this eigenfunctions functions in Rn. This is a work here, Granchev, Filipovich, and Rodino. Of course, I'm sorry. Of course, this is a short introduction to Gelfand-Schilov space, but there is some a number of papers and books, good reference for this study here. For example, there is this book by Rodino and Nicola, the chapter 6. The book is Global Calculus on Rn. I'm not sure anymore of the title, but it's a very nice book. The chapter 6, there's some nice introduction to Gelfand-Schilov space and some properties. Okay, but talking about this expansions, in this work, they consider this differential operator here, the final of order greater than 2, satisfying this condition here, and also some this elliptic property here, right? Well, under this hypothesis, it's possible to obtain some expansions, but a basic example of an operator satisfying these conditions is the harmonic oscillator minus the Laplacian plus x squared. In this case, the eigenfunctions are given by some Hermite functions here. Okay? This is the simple model for this 2 and 3. right? But for the general case, it's possible to obtain, of course, here, for this case, for these expansions, I will consider the symmetric case, the symmetric Gelfand-Schilov space, okay? And for this operator P, we have a basis. Also, we have some Weyl formula, very important, okay? And given a function on L2 or even tempered distribution, we can spend this Fourier series here, okay? So we have this ingredient on the variable x, and what we did was combine this result with a periodic on T, and in x belongs to Rn by using this expansion, right? And of course, we have a nice characterization for the symmetric Gelfand-Schilov spaces. This function, a function belongs to this space if we have some this nice decay here for the Fourier coefficients. You see, in this case here, we see that mu is the Gelfand-Schilov regularity. And here we have some dependence on the dimensional of we are considering Rn, right? Well, let's start talking about this time periodic Gelfand-Schilov space, okay? So given the sigma and mu satisfying this condition, I will define this S, sigma, mu, and C for the positive constant C. First, this space here, smooth functions, satisfying this estimation, okay? It's essentially, as I say, Gevrey on variable T and Gelfand-Schilov on the variable X, right? And we can do a lot. We can say a lot about these spaces here. For instance, it is a Banach. We can define now S sigma mu as this union of these spaces. We can equip with this inductive limit topology. We can obtain informations about convergence. In this case, a sequence converges to phi if there exists a constant, such that these functions belong to the same space, and we have convergence on the norm. Okay. Okay, and of course we can define the S prime sigma mu as the space of linear forms. Sorry. From S sigma mu to C, satisfying this estimated. For every positive A, there exists a constant satisfying this estimate, right? Okay. Now, let us to obtain some characterizations in view of the Fourier analysis generated by this orthogonal base phi j. Okay. We need some previous results here. Two lemmas. Firstly, is that F belongs to this space here if and only if there exists A and C satisfying this estimate. Okay, we have here some factorial properties here with the mu and sigma, and also some extra result here. It's essentially a comparison between the polynomial and the exponential. The proof is very simple, and I will skip. Okay. Right. First proposition is the following. We have start with this U belongs to the S prime. Okay. And we can prove that U belongs to the S sigma mu if and only if there exists some constant satisfying this estimate here. Essentially, we have here powers of the operator, the elliptic operator M. Okay, this is the first step here. We are comparing this space with the powers of the elliptic operator. Okay, the proof I will show only some ideas from this part here, the necessary condition. The converse is not it's not hard, but it's necessary a number of estimators, and I prefer to restrict myself to this simple case here. Firstly, given some m, some natural number, the power of m is essentially the same operator. The difference, of course, we have a bigger order here, and of course, new constants. But it's possible to obtain some controls for these constants here, right? This constant c is independent of m, right? And now, by using this estimate here, 7, okay, this supremum here, we can use the L2 normal of this guy, is this L2 normal of this guy, and then by using 7, okay, we obtain this estimate here, right? So we are usually essentially here some functional analysis here, okay? Right, the next theorem is interesting, okay? We start with U belongs to some S prime, and we can prove that U belongs to the S if and only if you can represent as this series here, right? Where this UJT is a sequence belongs to some Gevrey spaces. Of course, it's possible to see this explicitly this sequence and satisfy this condition. There exists a positive constant C and epsilon satisfying this estimate, right? Essentially, here we have some Gevrey regularity, and here some Gelfand-Schilov decay, you see? But in this case, of course, depends on the regularity, mu, and also the dimension of the space, okay? Some sketch of the proof. Let's assume that U belongs to S mu, okay? Then by fixing T and K, we have this derivatives belongs to the, let me say here, the standard Gelfand-Schilov space, the symmetric Gelfand-Schilov space. Then you can use the Fourier expansion given by the reference, Filipovich, Grantchev, and Rudino. We can then define AJK as this product here, this L2 product, right? And then by using some equalities here, using the powers of the operator P, by using the Fourier expansion, we will get, and here by functional analysis, we have this sum here. But the previous proposition, we have some boundedness for this term here, right? That means we can obtain some boundedness for this guy, right? And then you can estimate the supremum of that sequence AJK, okay? Here it's important from this point to this. We are using here for lambda day that veil formula, okay? Right. And now, of course, it's a question to take the info on the right side, and we will obtain the exact estimate. Okay. So this side of proof is very simple. Conversely, we consider it as we assume that U is given by formula 10, with UJ satisfying that condition 11, right? And again, by using the powers of the elliptic operators and some functional analysis here at some point, we get this inequality, right? And by using the hypothesis, we will obtain the estimate, okay? So we have some characterization for this space here. L starting in S prime. We know whenever with this, we know when this function is in this distribution here is indeed a function, right? Okay. Well, some extra results, essentially in order to obtain some uniqueness for this Fourier coefficients, right? Okay. some technical results, some characterizations. For instance, this theorem for here, if we start with a sequence of Gevrey distributions here, satisfying this condition for a given epsilon and age, there exists constant satisfying this inequality, then we can prove that u given by this function here belongs to the distributional space of sigma mu. Okay, this is also a consequence of this previous results. Okay. Right. So we have therefore we start with some this function that is time periodic Gelfand periodic in T and Gelfand of X. Okay, we have all characterizations for these spaces, and we can then apply to this hyperelliptic problem. Okay, is essentially the study of this this operator here. Okay, so L is dt plus Ct px dx. Here px dx is that normal operator, that elliptic operator, satisfying condition 3. Here I will assume that C is a Gevrey function on the torus. And of course, here sigma is strictly greater to 1 because at some point it's necessary to consider cutoff functions, right? This is the reason for this restriction. Okay, now let me consider just an annotation here. This F here, F mu is the union of the functions, and U mu is the union of these distributional spaces here. Okay, right. Then we have the definition of global hyperellipticity. We say that L is S mu globally hyperelliptic. If we start with U belongs to U, capital U, and U belongs to capital F, then U belongs to F mu. The reason for this, I'm considering this union here, is because it's possible the existence of some loss of regularity. I mean, if I start with F belongs to F belonging to S sigma mu, and if the operator is globally hyperelliptic, maybe U belongs to some class here S theta mu, for theta different from sigma. Okay, but I will show this in the next slides. Right. Okay. Consider then U. Solution of this problem, ILU equals to F, by using the Fourier expansion. The equation is equivalent to this system, the sequence of ODEs, right? And we can prove here, if you consider C0 the average of the function Ct, we can prove that Uj belongs to the same Gevrey class as the coefficient Ct for all j. And when lambda j C0 is not an integer number, we can show that the equation 17 has a unique solution, and you can write in equivalent two ways. This different ways here is because at some point it's necessary to consider lambda j negative, lambda j positive, or the imaginary part positive or negative. And this is the reason I'm considering this equivalent two ways here. Right. Therefore, if what we need to do is to show that the solutions of equations satisfy this behavior here. I mean, L is S mu GH if and only if there is some theta, C, and epsilon satisfying such that the derivatives of the coefficients Uj satisfy this estimate here. Okay, here theta should maybe is different from sigma, the regularity of the function f, because it's possible this instance of loss of regularity. Okay. And of course, what we need to do to study the solutions here, right? These expressions. Here we have the essentially some Diophantine approximation. Here we have a problem with the possible change of sign for the imaginary part. Okay. And let me show you the results we will obtain in this case. For instance, start with a constant coefficient. Consider L dt plus alpha plus I beta, px dx, and this set here, the set of j such that this term here belongs to 0. First result, if L is S mu globally hyperelliptic, then the set is finite. Okay, so if we are trying to prove that L is global hyperelliptic, we can assume that the set here is finite. And here we have something interesting. We need this definition. We say that a real number is not a mu exponential Liouville with respect to the sequence lambda j, if for every epsilon that exists, C epsilon satisfying this inequality. You see, the problem with this expression here, this definition is somehow familiar for a number of you, because it's connected with the study of global regularity and on the torus for when you are considering the setting of Gevrey functions, right? The difference, of course, is now we are comparing the number with the sequence, lambda j, the sequence of eigenvalues of the operator, okay? And also we have here, of course, mu is the regularity, the Gelfand-Schilling regularity, and also we have here n, which is the dimensional of the space, right? So we have some connections between the usual case, but some novelties here. The dimensional is important here. Okay, the first here, so for the constant coefficient case, the operator is globally hyperelliptic if either beta is different from 0, or beta is equals to 0, and alpha is not mu exponential Liouville with respect to lambda j. And the proof is somehow simple, because you see, the solution of this problem, of these equations, is given by this these expressions here, right? And okay, for beta different from 0, it's not, this term here is not important, okay, because in some sense he's far from 0. Of course, here we can assume, when you consider modulus of this exponential, we have exponential of S beta lambda j. So if beta is negative and the lambda j is positive or converse, it's just to interplay the solutions 23 by 24. But in this case, for beta different from 0, it's easy to see that all derivatives of uj is essentially less than or equal to the supremo of the derivatives of fj. That means uj, the solution u belongs to the same class as f. When we have beta equals to 0, of course, we need to study this quantity, right? But then we have the control for this constant here in view of the exponential Liouville hypothesis here, okay? But in this case, when we have constant coefficient operators, there is no loss of regularity on variable p, okay? I mean, if LU is S sigma mu, then U belongs to the same class, sigma mu, okay? Different from the case of variable coefficients, okay? A simple example, if you consider here the harmonic oscillator on R, in this case, the eigenvalues lambda j is 2j plus 1, and the exponential reveal hypothesis is given by this expression here, okay? So it's possible to obtain some nice examples. Well, for the general case, with non-constant coefficients, okay? Let's put here CT as AT, IBT, and the corresponding A0 plus IB0. We have here, for instance, if L is S-me global hyperlipid, then the set is finite. It's connected with the solutions of the respective ODEs. This constant operator is global hyperlipid, and the main theorem is this one. This operator here is global hyperlipid if and only if the imaginary part does not change sign, or if BT is equal, here is does not change sign and is not identically zero. And part B, if is identically zero, and A0 is not a mu exponential reveal with respect to lambda j. Almost this, essentially the same as in the differential case for the torus. The difference here is because we are considering this mu exponential condition with respect to the sequence. Okay. Just to show you where is the loss of regularity. Okay. I will skip the case of some case here, especially what we need to do to prove that if there is change of sign, why the operator is not global hyperliptic. Well, it's possible to construct some singular solutions, okay? But I will show you just some ideas for this case here. Assume that B is not identically zero and does not change sign. Okay, and in this case, we start with this equation, I L U equals to F. Since BT is not identical to zero, and does not change sign, we can assume that B0 is different from zero. That implies the set Z is finite. In this case, we may consider expressions 18 and 19. Okay. And since B0 is different from zero, there is no problem with this part here. This sequence theta j, neither the sequence capital gamma j. Okay, right? So what we need to do is the study of this exponential. Firstly, by using Leibniz, the derivatives of uj is given by this expression, right? And in order to obtain estimates for the derivatives of this exponential, I need a Fadi-Bruno formula, okay? The derivative of this exponential is then given by the sum, right? And of course, this is the derivatives of the coefficient of the operator, but it belongs to some Gevrey class on the torus, and it's possible to obtain this estimate, right? Therefore, the estimate for these solutions now, it depends only on this term, okay, and on the behavior of the Fj. But Fj, we know the initial data F belongs to the S mu sigma, S sigma mu. So we have control for this guy. Okay, since here I'm assuming that lambda j is positive, I'm using Veil formula. Since lambda j is positive and I assume that b is negative, this exponential here is less than 1. And we obtain now this estimation for uj. Here, I'm using the conditions on fj, the existence of this epsilon 0, right? Here, I'm using that lemma 2. We can estimate this part here, this JLM by this exponential. We can estimate by using this inequality here. Therefore, finally, all derivatives of uj are less than or equal to this constant. And here we have gamma factorial power the max of sigma or m mu, right? Well, in this case, we have that u belongs to this space, implying that L is globally hyperelliptic. However, in this case, we have loss of regularity, okay? But this loss here, right, of course, depend on the Gelfand-Schilov regularity on the variable x, and also depend on the order of the operator. Okay, so we have here for several classes for several cases, we have some loss of regularity. Okay, depending on m and mu. So we have the loss on variable t depend on properties of variable x, in short, right? Okay, an example here, we can consider again the harmonic oscillator, and the case considering AT plus IBT, okay? And it's possible, for instance, if B is equivalent to equals to 0, then the operator is global hyperelliptic if and only if A0 is not mu exponentially. And it's possible to obtain some examples of this A0. Okay. Well, this is only what I have to share to you today. Thank you very much for your attention.
Thank you, Fernando. Questions or comments? Just a curiosity, this results about hypoelectricity, of course, it's connected with solvability results. And in your opinion, it's possible to use, in the case of tube case, it's possible to obtain solvability in this kind of
yeah,
space?
I think yes. This is the next step of our collaboration, Capello. You are thinking about the solvability and also for some high order equation. I mean, instead of dt, some dt power m, and also some Cauchy problems. But I think it's possible. I agree with you.
Thank you. More comments or questions? If not, let us thank Fernando. Thank you.
Stop sharing.
Gabriel?
Okay.
Okay.
Can you see my screen, Paulo?
Yeah, it's nice. Okay, the next speaker is Gabriel Araújo from University of São Paulo at São Carlos, and he will tell about invariant involutive structures on Lie groups.
Thanks, Paulo. It's a pleasure to be here in the Colóquio. It's my first time in the Colóquio, actually my first time in Rio. The weather is lovely. And thanks for the organizers for the invitation to be here today. I'm going to talk about a class of involutive structures, which are systems of vector fields, which have many symmetries. So that's why we'll be talking also about Lie groups. First, involutive structures, they're actually a language, a good language to talk about systems of complex vector fields, which, according to the main theme of this section, we regard as first-order differential operators, partial differential operators. For technical reasons, in order for this theory to work properly, we have to look only at systems which convey the maximum quantity of information, meaning if you take commutators of equations you already have in your system, you don't get new equations. So what one way to express this is to impose that our system of vector fields is closed and under Lie brackets. Okay. As I said, this can be regarded as saying that our system of equations is somehow complete. And we encode all this information in a geometric object, which is a vector bundle. We will take sub-bundles of the complex tangent bundle of a smooth manifold, and such bundles will be called involutive whenever the Lie bracket of any two local sections of our bundle is again a section of our bundle. These sections of our vector bundle will be the vector fields in our system. Okay. Okay. And this kind of object, these involutive vector bundles, they occur very often in many fields, but especially in complex geometry, where most of the examples we usually study come from. And if you don't know much about it, you can just think of the Cauchy-Riemann operators in several complex variables. They are complex vector fields that, of course, commute. Okay. So about this object of involutive structures, we already have two classical textbooks, one of Travis and one to these three authors, and there are a lot of topics regarding the systems of vector fields are dealt with. But among them, which is the one thing that is of interest to me here, it's how to associate to an involutive system of vector fields a differential complex, which plays a role vis-a-vis with the Run complex in differential geometry, or the Bose complex in complex analysis. Okay, and And this differential complex is can be regarded as a way to pose and say algebraically all the possible ways in which we can combine in a meaningful way all the vector fields that appear in our system in order to produce matrices of differential equations. Okay, just to give you two simple examples of this kind of feature, let's say I take n complex vector fields which commute. Well, a simple problem I can associate with them is this. Give a single function f, find me functions u1 to un such that this equation can be solved, okay? But I also can combine these vector fields in order to form other kinds of equations. For instance, this one. I give you now n functions, f1, fn, as my right-hand sides, and I want you to find a single function u solving all these equations, okay? This is the same u for all of the f's, okay? Now, however, compatibility conditions, they appear. A necessary condition is, of course, because these vector fields commute, is that the right-hand sides must satisfy all of these equations. If the fj's don't satisfy these equations, your search for a u to solve this system is just hopeless. And these conditions arise because the vector fields I started with, they commute, okay? So instead of presenting here the abstract definition of what would be the differential complex associated to an evolutive structure, I will show concretely the equations that arise, provided we put a simplifying assumption on our system, is that it has lots of symmetries, okay? And our point of view will be global. It's inherently global because of the symmetries. We start with the Lie group, which is a smooth manifold in which you have operations that turns the manifold into a group, and the operations are smooth. And I will denote by L sub x the left translation by an element x. And we recall that a vector field on G is said to be left invariant, provided that whenever I push forward the vectors by every possible left translation, I reach the same direction assigned by the vector field x, but at a different point, okay? And not something else. Essentially, when I push forward x by any left translation, I get back to the vector field x itself, okay? And I will denote it by this German G, the space of real left invariant vector fields, and by C tensor G, the space of complex vector fields. And we know that these are Lie algebras, meaning that whenever I take the commutator of two elements in these spaces, they are again elements in these spaces. And we have these isomorphisms, which we usually learn in introductory course in manifolds. Okay. Some examples: tori, they are Lie groups. They are compact and connected Lie groups, which are also abelian. Okay, the group operation is commutative. And left invariant vector fields on a torus are precisely vector fields with constant coefficients. Okay, and which were extensively studied by Greenfield and Wallach from the point of view of PDE. And we should keep this work of Greenfield and Wallach in our minds as we go on. Okay, so let's talk now about systems of vector fields. And just as a single vector field corresponds to an element in this space, I'm thinking about complex vector fields, okay? Then subbundles which are left invariant, without being really very formal here, they correspond to linear subspaces of this complex Lie algebra, okay? And then involutivity, which is being closed under brackets, is translated into this linear subspace being actually a Lie subalgebra. Okay, so this is what I'm saying here is that to left invariant and involutive subbundles on a Lie group, they correspond in a one-to-one fashion to Lie subalgebras of the complex Lie algebra of G. Okay, so this is our main object of study. With this in mind, I can show you how the equations that we are interested in, they present themselves. So I take the Lie algebra associated with our system of vector fields. We take a linear basis of this as a finite dimensional vector space. They don't commute in general because I'm not assuming that my Lie group is an abelian. And I complete them to a full linear basis of our complex Lie algebra. Okay, this also don't have to commute in any sense. And so since the L's and the M's, they form a basis of this vector space, the dimension of our Lie group is M plus N, okay? And then we look at the dual basis of in G star, actually in the complex G star, which is dual to these vector fields, okay? These are actually left invariant one forms, okay? And given a Q, I will denote it by this space, infinity of G, comma, lambda Q, the space of all complex Q forms in G, which contain no zetas, okay? They can be expressed globally as combinations of exterior products of the taus alone, okay? With some smooth coefficients, okay? Here the notation is the traditional one for some multi-indices, order multi-indices. We denote by tau j this exterior product, okay? And I want to define an operator d prime which maps the lambda q to the lambda q plus 1, which is related to the exterior derivative on G. So what do? We pick an element here which has this form and apply the exterior derivative. So we go on applying the exterior derivative, and this part here we copy here, and this part here we expand, and we got this. But now what happens is that zetas appear. So we must project everything back to the lambda q plus 1. And how do we do this? We simply delete every occurrence of any zeta k. Zeta k's they definitely appear here, but they might also appear here. But because all of these are left invariant 1 forms, we can prove that the differential of the tau j, they can be written as a combination of tau k's with constant coefficients. They must be complex because these are complex 1 forms, plus terms containing at least 1 zeta k, which we just ignore because we are trying to project this expression back to the set of forms that contains no zetas. So we just throw them out and we rearrange everything conveniently. And we reach this expression, okay? Where here we have constants multiplying the coefficients uj, and here some signs appear just so we can bundle the coefficients together to pair with the tau case. This is how we define our operator d prime, okay? And what we have here is actually a matrix of first-order differential operators. The entries of the matrix are these guys, okay, with real analytic coefficients, okay, because the zero-order terms are just constants, and the first-order terms are vector fields, which we assumed were left invariant, and because of that, they are automatically real analytic. And also, one can show that they form a differential complex, meaning that when I apply d prime twice, this is 0, okay? So this is the problem that we want to address. When I have f an element in lambda q, I want to find u an element 1 degree less, such that d prime of u equals f. And here, just as in the simplified example, compatibility conditions arise because since d prime square is 0, a necessary condition for the existence of solutions of this equation is that d prime f equals 0. Okay? I will give just a simple example here when such structures arise. So take M to be a Lie group with Lie algebra small m, and take as G the product of M with a circle. Its Lie algebra is just M O plus R. And take omega, a left invariant 1 form on M. And we denote by x the angle coordinates on the circle. And I'll take as zeta this 1 form minus omega plus dx. We regard both of this is in the circle. This is in M. We regard them as elements in the product, okay, as 1 forms in the product, so I can sum them. And this is the left invariant 1 form on G. And it defines an involutive structure V by declaring that X is a section of V if and only if X is a vector field that is annihilated by this 1 form. And this defines a left invariant involutive structure with the underlying Lie algebra is precisely this set of, this star is just a typo. the set of complex left invariant vector fields, which are annihilated by this one form, okay? And concretely, if I take T1 to Tn a basis of M, and tau1 to tau1 the dual basis in M star, I can write omega as a combination of tau j's, because this is a basis of one forms, with constant coefficients, because I'm assuming omega to be a left invariant one form, in which case I can prove that a basis for our underlying Lie algebra is formed by vector fields of this form. Okay, this is very familiar for, this will sound very familiar for people who work with tube structures. Okay. Now we go back to the general case, and some questions that are of interest to us. One is to determine when the map D prime has closed range. We're dealing with the global phenomena here. Another thing is that since we are dealing with a differential complex, is to study the cohomology spaces of this differential complex. So we can ask a bunch of questions about these spaces. For instance, does it vanish? Which is just a way to deal with the question, is the equation d prime of u equals f always solvable, provided, of course, f satisfy the compatibility conditions? If not, is it finite dimensional? That's another interesting question. And as is usual in this business, we can also change these questions and to put other classes of coefficients, say real analytic, Gevrey, or distribution, or whatever it seems fit, okay? Good. So let's recall a little bit some results due to Greenfield-Wallach for vector fields. This is the standard vector field on T2, where we're assuming the coefficient to be rational. And Greenfield and Wallach then characterize global hypolepticity in the two torus of such vector fields. It's in terms of an inequality of this type, which is the same as saying that alpha is not a Liouville number. And in the same volume, Greenfield also has a paper all by himself dealing with the analytic version of this. And he characterizes global analytic hypolepticity of these vector fields, which is in terms of a more elaborate inequality. And this is the same as saying that alpha is not an exponential Liouville number. But this inequality implies is implied by the previous one. So in particular, whenever L is globally hypoleptic in the smooth sense, L is globally analytic hypoleptic, okay? This is the first result that we are going to, we generalized for these involutive structures. So the next result we might regard the next result as a sort of Greenfield and Wallach on steroids, okay? Take a compact connected Lie group, not assuming to be the torus, but still compact, and take not only a single vector, not a single left invariant vector field, but a system, which for us is a left invariant involutive structure. the result we reached is that whatever the degree you look at, whenever D prime has a close range in the smooth setup, then it also has a close range in the real analytic setup. Okay. If the cohomology space in the smooth setup is finite dimensional, then also is the cohomology space with real analytic coefficients. And in that case, they are isomorphic. They have the same dimension. And also, just because we can also replace real analytic in these statements by Chevrolet classes, or even more exotic ultra differentiable classes. Okay, the statements are just the same. Paulo, how much time do I have?
5 minutes.
5 minutes, okay.
Yeah.
Okay, so in these last 5 minutes, I will try to explain another kind of result concerning these left invariant impulsive structure, and recall that the left invariant form, a Q form is left invariant, provided it's pulled back by every possible left translation gets you back to the same Q form, okay? So, for example, regarding our forms that can be written involving no zetas with respect to, say, to some involutive structure, then this F is left invariant if and only if these coefficients are constant, okay? And these now quite old result, and I guess it's perhaps it's not even due to Chevrolet and Eilenberg, but it's contained in this paper, which has some original material, but it's actually a very readable survey of the state of the art of these of Lie groups and Lie algebras at the time. And it goes like this: if G is a compact and connected Lie group, then every closed form has a left invariant representative in the same cohomology class, meaning that for all closed Q form, I can find a left invariant Q form, which we should think of them as forms with constant coefficients in some sense, such that F minus G is exact. This is a statement about cohomology classes in the RAM complex, and it implies that among other things that all the RAM cohomology spaces are finite dimensional, but this is true for compact manifolds in general, but if you don't know that result, well, then you get it from this. And recently, Young, in his PhD thesis, he conjectured that some analogous results should hold for elliptic left invariant structures, okay, on compact Lie groups. And he attacked many particular cases of this conjecture, and I will show you a simple result in this direction. So back to our setup. G is a compact and connected Lie group. V is a left invariant involutive structure, and V, and small v, it's the underlying Lie algebra. and using analysis, which is a elaborate form of Fourier analysis, and a pinch of algebraic theory of Lie algebraic cohomology, we could prove the following particular instance of the conjecture of Young, which is the following. Suppose that our involutive structure is elliptic, which algebraically we can read ellipticity like this. The sum of V with the complex conjugate of V is the whole Lie algebra. And we put an extra ingredient, which is an algebraic property on V that is semi-simple, okay, which is something related to the ideals contained in V. Then whatever F in lambda Q smooth, there exists a D prime closed, whenever F is D prime closed, I can find a G in lambda Q, which is left invariant and also D prime closed, such that F minus G is D prime exact, which is the precise generalization of this, but adapted to this more general involutive structure. Not for the lack of example, whenever we deal with, when M is a semi-simple Lie group, all these tube structures that we defined in the previous slides, they have this property of being semi-simple. And if you put some extra condition on the coefficients, you get that they are also elliptic. So for these structures, this theorem applies. I think I'm on time. And thank you very much. That's all I have to say about this.
Thank you, Gabriel. Questions, comments?
Gabriel, for this kind of result, you have something for double complex, or that means try to study solvability in some sense?
Yeah, you see, you mean double complex and from complex geometry, right?
Yes.
Yeah, but well, in that case, the structure is elliptic.
Right.
So for instance, the first result that I mentioned about closeness of the range and finite dimensionality of the cohomology spaces, they all apply. Because the D prime has closed range on smooth coefficients, and actually the cohomology spaces are all finite dimensional. Regarding this second result, well, actually we don't have many examples of structures that satisfy this algebraic property. Okay. So
does not fit in this case.
Yeah, I never thought about it. I don't know if there are examples of probably are examples of complex structures that are semi-simple. I'm pretty sure there are, but I never. Max Janke dealt. He studied that kind of thing much more deeper than I did. Perhaps he's much more knowledgeable. About this. I think probably yes, but I'm not sure.
Okay. Very nice work.
More comments or questions? If not, let me thank Gabriel again. Before the people leave this room, as I mentioned before, this room will keep open for more than 1 hour. But if possible, the people could open the camera just for a print screen for records. Oh, nice.
Several no people. Hi, Bruno.
Hi, Professor. How are you doing?
Fine. You. Oh, Vanderlei, Paulo. Nice. Luis.
Okay, thank you.
Okay.
I did the print screen. I can send forward by email.
Thank you.
So we return with our section on Thursday in Brazil time, 2:30 p.m. Okay.
Fine.
And now the room will be open for some time. I don't know. Depends on your convenience, your time. Okay.
Fine.
Very nice talks. Olá, Paulo.
Oh, o colóquio 3 é identidade secreta.
Colóquio 3, colóquio 3 esse é o...
O Sueli sou eu aqui, ó.
A Sueli testa.
Eu não conseguia conectar no começo, rapaz. Eu fiz de tudo aqui, entrei no colóquio, ensinei todo mundo como conectar e o meu não conectava. Daí eu liguei lá para o colóquio, mandei uma mensagem, eles responderam que estava com problema na minha inscrição. Não registraram lá eu não paguei, talvez.